Test, test, test. Alright, I don't know what happened there. Let me test this recording here. 1 second. Yeah, something got fucked up with this mic. If I go to properties here, it says Ryzen. Properties here, it's also Ryzen. Alright, well I'll just mute it. Hopefully everything works with stream. Okay, so I just wanted to hop on real quick for maybe an hour or so to work on not the stuff that I was working on yesterday with CSAPP, but let's jump over to here. There was a systems design interview problem that someone sent me from Anthropic, and I wanted to flesh out some ideas around that because it seemed like a really interesting problem. Let me pull it up here. Give me 1 second. So here's the problem. Let's open up Excalibur and just oops. I'm just gonna save to disk. Desktop, home, desktop. Is there no desktop? There it goes. More Excalibur, save, and then I'll just blow away all this. Reset the canvas. Confirm. Okay. So let's type out the requirements. So this is what I got from here was requirements are 500. So the basic problem is you have a 500 gigabyte file and you want to basically blast that out to thousands of servers, and you want to optimize for the amount of time it takes for the overall process. So 500 gigabytes file on a single, come on, sorry my typing's not great this morning. Need to transfer that to 1000 servers. Servers have a 10 gigabit NIC, and you want to optimize for transfer time, single region, single DC, and traffic is on private in. He said private internet. I think he meant intranet. Okay. Just want to make sure that I got everything. So I was thinking about this last night and this morning a little bit, and I was thinking this would be an interesting problem to actually solve, to actually create a software artifact that can solve this problem. And there's a bunch of different approaches that I was thinking of. The first thing that immediately came to mind was using some type of UDP or IPv6 multicast. And the downsides of that are that first, your network has to support multicasting, which most commodity hardware, networking hardware will support multicasting. But if you're in a cloud environment, I did a little bit of research, and AWS doesn't support multicasting on its VPCs. You have to use Transit Gateway to get multicasting. So that solution basically doesn't work for cloud environments because there's no network hardware support. So I was thinking, okay, well, I guess what are the trade-offs if you did have support for TCP/IP? Sorry, for UDP. I guess you can do TCP as well, but basically, if your network does support multicasting, what are the benefits and drawbacks? The benefits are that the networking hardware does all the copying for you. So on the sending NIC, the broadcasting NIC, you're saturating 10 gigabits out into the into the network. The network does all the packet duplication, and then on the receiving ends just have to receive all that data. And so it's super optimal from that perspective, because the client and the server are just kind of dumb to all the duplication of data that's occurring for them. The downside is that you're putting a lot of stress on your networking infrastructure. So, this is 500 gigabytes over 10 gigabit NIC, fully saturated. That's like a lot of data to be duplicating across 1,000 different ports or whatever. Obviously, the duplication, the multicasting stuff is done in hardware, so it's like super optimal already. But you could run into situations where you saturate your networking infrastructure and then your network's hosed. Basically, you're DDoSing or you're denial servicing your own network. So that's a potential risk. So you have to have that networking support, and you have to have a network that's capable of doing all this data duplication without hosing your network. There's one other downside that I was thinking of, but I can't remember it at the current time. Just packet loss and retransmission. So because multicasting is working on IP frames and potentially UDP datagrams, you're going to get packet loss or datagram loss, and that will require retransmissions. So basically you need to invent some type of sequencing on top of this. I know there's projects out in the world already that do these type of things, but for the most part, they're not very up to date. I did a little bit of research last night, and this technology seems to have gone out of favor at some point, the multicasting technology. So, while it's a really optimal result in that you can theoretically fully saturate your transmit from the machine that has the data, and then all the other machines just have to receive, and everything else, all the duplications handled by the network itself. Like, that is an elegant solution, a very optimal solution from the perspective of the transmitters and the receivers, because the network's doing all the work for you. But then you also have to layer on top of some type of reliability guarantees with sequencing IDs, retransmissions, stuff like that. So those are all the downsides. For a cloud environment, it's really like a non-starter, just because they don't support any of this stuff. So, assuming we're in a cloud environment, how would you go about doing this? So let's think about doing this diagram really quick, where you have on this side, we'll just say like node, we'll say n sub x. That'll be our node, and we'll have n sub 1. And how do you do like sub? I guess I can do like small? No. Oops. I guess that applies to the entire thing. So can I do any type of, what is this thing? Font family. Oh, it's saying code. And these are presets, I guess. Layers, opacity, maybe up here. Doesn't seem like we can do it. So it's pretty simple text here, but we say n sub 1 here. Or we say n sub 0 for the 0th node. N sub 1, n sub 2, and then dot 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 all the way up to n sub n minus 1. And then each one of these we're going to have time on this axis. So I'll just go ahead and do another thing here. So it's time t, and it goes in that direction. And we're going to color these whether they transmit or receive. Sorry, background. Can I do no stroke? We'll do roundy. Yeah, we'll do it like this. Cool. And we'll call this thing TX. And then we'll have another one of these that we'll call RX. And we'll just make this color like blue here. Okay, so one approach would be to have your server, which is N0, just completely saturate its outbound. And say it takes this unit of transmission time to actually transfer the 500 gigabytes. So if we did a little bit of calculation here, we'll say total transfer time. One time transfer T is equal to, well, we got 500 gigabytes divided by the 10 gigabit connection per second, which would be how many seconds. One thing I don't like about Excalidraw, I guess you can draw like this, but it's really hard to do like math. So T is equal to, you have to do it in text form, which is kind of not fun. But this is going to be in units of bytes. Per bits per, so we're in gigabits, sorry, and then we have second here. So the seconds come up here, and then we have to convert gigabits into gigabytes. So byte is 8 bits, so it's 8 times that number of bits. So this is going to be equal to 8 times 500 divided by 10, and you're going to have seconds up here, and then the units for these two cancel out. So that's going to be equal to 8 times 500. Let me just bust up my calculator here. 8 times 500 is equal to that amount, 4,000. So it's going to be 400 seconds. So each one of these units is 400 seconds. Just highlight this, make this in bold. Can I do one section in bold, or do I have to like do the whole thing? I think it's the whole thing. If I do this and hit Control B, yeah, it doesn't work. Okay, that's fine. So maybe we do a little like T0 here, and then we'll just say 0, 500, or sorry, 400 seconds, 800, and then this will be 1200 seconds. All right, so in our first iteration, we're just gonna do a whole file at a time. I think the ideal solution will be pipelined with chunks, where a server is doing both sends and receives to get the file out there. But just for the initial kind of like idea here, so once we hit this point, N0 is then free to transfer to N2, and N1 is free to transfer to N4. So we'll have a stack like this, basically. So this is going to be N4. We'll do N5, N6, N7, N8. And we're going to have 1,000 servers. So this will be 999. Okay, so at step 2, we're now receiving on 2 to 4. Step 3, we'll be receiving on, actually I'll just copy both of these at the same time. Boom, boom. These will be transmitting, and these will be receiving. So each unit here, so T0, the state at T0 is one server has it. The state at time 400 seconds is 2 servers have the file completed. This will be 4 servers have the file completed. This will be 8 servers have the file completed. So you can see it's like an exponential growth here, which is a nice property. We can do better, but for the initial kind of like example here, let's go ahead and develop an equation for this. So I'm actually gonna pull this out of the requirements section, put it over here. We will delete all this stuff, put the requirements over here. This guy needs to go back to being white, thank you. So one-time transfer time. It's still a little bit of math here for total transfer time. So it's going to be based on the number of servers. So we'll pass that in as n. So T of n would be 400 times 400 seconds times um, 2 to the power of n. Pretty sure. So let's do a kind of case study here. We'll assume the 400 seconds, so 2 to the power of n of n1 would be 2. 2 to the power n minus 1. So it would be n minus 1. So 2 to the power of n minus 1 if we have one server, I think it's actually going to be -2. I think the -1 has to go out here, like that. So we would have 2 to the power of n minus 1. So n is, we'll do some worked examples here and make sure that they align with our diagram. So 2 to the power of n, so it's going to be 400 seconds times n minus 1, so this is, n is 1. So 2 to the power of 0 is 1, 1 minus 1 is 0, that's 0 seconds. So let's do 2. So that'd be 2 to the power of 1, which would be 1. Wait a minute. 2 to the power of 1 is 2. -1 would be 1, so that'd be 400 seconds. 400 seconds. If we had n is 3, this would actually be n is equal to 4. We'll come back to 3 because my math is a little bit off here. Okay, so 4 would be 2 to the power of 3. 2 to the power of 3 is 2, 4, 8. -1 would be 7? Doesn't seem right. Yeah, let's go ahead and just do the last example here, and then we'll work back from there. So it's going to be 400 times 1, 2, 3, 4, 5, 6, 7. So we want this to be 8. Actually, it's going to be 3. 400 times 3. So what is this 3 going to be? 3 is going to be log of n, I believe. Log base 2 of n. ln of n. I'm supposed to open a calculator. So can I go to advanced? Yeah, let's do advanced. That's not advanced programming. LG of 8. Because ln is a natural logarithm. I want a log base 2. How do I get a freaking log base 2 on this calculator? Mathematics? These are constants though. I want a log base 2. That's trigonometry, complex, programming, rounding, no. Statistics, no. Here we go, log base 2 though. Oh, you can do the base here. Okay, so you say log 8, 2. There we go. Okay, that gets us back 3, and that'd be 1, 2, 3. So that looks like it's correct. So it's 400 seconds times the log base 2 of n. Log 2 of n. So in this case, it's 8 goes to 3, 400 times 3. Which equals 400 seconds times 3, which equals to 1200 seconds. Let's do 3 here, or 4. I guess 4 would be the natural thing next here. And we have to round this, I believe. We can delete this because that's redundant. So it'd be 400 seconds times, we'll do log of 4 base 2, which gives us back 2. Oops. Which is equal to 800 seconds. And then 3, this is where we're going to have to do the rounding. So log of 3 base 2 is 1.5. So we'll have to round up. So that'd be ceiling. There's like a ceiling function here. I saw it earlier. Rounding, here we go. Ceiling, C-E-I-L. So ceiling of, ceiling of log 3, 2. Wait a minute. Yeah, 2. So we need to wrap this in a ceiling. So that would be 400 seconds times 2, 800. And then 400 seconds times, we'll do the same thing here. Put a pipe in 2 here, that'd be 1. 400 seconds. And then of course 0 seconds. Because ceiling of 1 is 0. Okay, so that works out pretty nicely. 400 seconds times the ceiling of log base 2 of n. That's the total transfer time of this solution. Now, something to observe is that a huge amount of the time, so if we plug this all the way into t is equal to 1,000, we can work out the total time for the entire transfer, theoretical total time for the transfer. So I'll just plug that in here, and we get 10. So it'd be 400 times 10 times, so that'd be 4,000. 4,000 seconds. 4,000 divided by, here's divided by 60. It's going to be equal to 1 hour. So we'll say approximately equal to this is how many minutes? 1 hour 7 minutes. Say 1H7M. That's a long ass time. And that's a theoretical best for this solution. So let's go ahead and try to do better than that. So let's actually move this over here, and I'll put this here, just group it with the solution. Okay. So let's chunk full file transfer, we'll say node chunking, and we'll make this a little bit bigger. Quit out of this. What size do you want to make this thing? Large, extra large? No, it's just large. And can I make it bold? Control B. I thought there was a way to make it bold. I guess not. Just larger. Okay, so we're going to do another one. We'll say half file transfer. And this will be 250 GB chunks. So let's do the diagram first, because I find that's like helpful to diagram out things first to get a feel for how they'll actually work. So in this case, we'll be transferring half, and we'll be receiving half, with the goal of getting, and we'll say tx of part 1. So it's tx1, or say tx0, just 0 index it. tx0 rx0. Now, what we want to do is say transmit 1 to here, but we also want to get this guy transmitting. So he's going to tx0. This guy's going to tx0 as well. So there's some complexity that's being added here. Because you can in parallel both transfer and receive, but only at half the rate. We'll just keep it simple. We'll say, okay, transfer 1 here. This will receive 1. Oops. So this one's transferring to here. This one's transferring here. This guy can now transfer to a third party here. I kind of like the halftime thing, but I can't make these any smaller. Unfortunately, I made them too big. So maybe we make this smaller. Will that allow me to do it a little bit? I'll have to make changes to this. I'm going to delete this whole thing. Make this guy bigger. The whole thing. I'll just like double its size here. And that'll allow me to make these smaller. Actually, if I go back, okay, that allows me to do it. Okay. So all these guys, I just need to make them, well, I'm going to delete all of these anyways. So he's going to transmit chunk 0. And he's going to do that for half the chunk. He's going to receive, let's make this guy small as well, Rx chunk 0. Then he's going to continue to transmit to two other guys, chunk 1. Because it doesn't matter what order he does them in. And it'd take him twice as long to do that. So the area has to be conserved here. So this can be now a receive Rx sub 1. Make that blue, boom, boom. And he's also going to transmit 0. We'll just identify the nodes here too. To N1, say N1, capital N1. And we'll read from N1 here. This will transmit T1 to N0. Sorry, N1 is receiving from N0. Say, hey, transmit yourself to N1. And then receive here from N1. He needs to transmit this thing to N2. And then he's going to also be transmitting 0 to where? We can probably go to N2 here as well. This will be from N0, N0 here. N1. Alright, I need to take a quick break here, but I'm going to come back and finish this diagram. I'll be right back. All right, I'm back. Tx0 to n1. N1 says Rx0 from N0. Yep, that's correct. And we did half the chunk, fully saturated both our connections here. Then this guy is saying, okay, I'm going to transmit chunk 1 to N1, who still needs it. So that's here. Now I'm going to do a little linky connectors here. Can I do that? What color should these things be? Like green? I don't like green. Let's do white. This guy is going from N0 down to here. Jesus Christ, this thing's annoying. See, what's nice about this is we're keeping it fully saturated, but we're also getting the chunks to them as quickly as possible. It would actually be better if we sent this chunk somewhere else, though, other than the guy who's receiving it. So there's two things that we're doing here. We're splitting our bandwidth between two different actions instead of having our entire capacity for one single action. And then we're also splitting the file in half into chunks, which allows us to do chunk-based sending. And I think these are two separate properties that need to be explored. Hold on, my freaking mic is like messed up again. It's not my day today. Alright, I don't think it's messed up. Okay. Yeah, I guess the thing that I'm like thinking about here is that we have two separate properties. One is using our capacity to do multiple actions, which you can do without chunking. And then the idea of chunking on top of it is like a separate property. And if we want to explore those mathematically as separate properties, it doesn't make sense to conflate them like we're doing in this diagram. So maybe we do chunking without chunking without the utilization, the splitting our utilization. Maybe we do that. Okay, let's go back here. And we'll say no split utilization. Okay, so that means that we'll have to do away with a lot of this stuff here. Okay. I'll keep the arrows. And say T sub 1 to N2, which will bring this guy down here. And we'll get we're just going to alternate here. I think that's a good strategy, alternating. Oops. Forgot to grab the connector. Oops. Alright, go here now. We'll say N3. Oh no, we can say N2 here, right? No, we want to go to N3. We want to keep on pumping it here. Oh, I forgot a 3 here. 0, 1, 2, 3, 4, 5, 6, 7, 8. So this needs to be N3 here. Which would be N3 over here. N3. And then N8 isn't necessary because we do it by 0. Yeah, we can eliminate that guy. Okay. So this guy needs to receive he has N0 now. Or he has the first chunk. So he needs to start sending as well the first chunk. Jesus Christ. Alright, so we'll do something like this. And then we'll bring this down somewhere. N2. I think we can go here. N3. N1. We'll say N question mark here. Okay, so now this guy still has only chunk 0. I think it'd be easier to visualize if we had some visualization for the chunks themselves. Instead of just labeling them T0 and RX, or sorry, RX0 and T0, yeah. I think we need some type of visualization like that. So let's zoom in here. I think we need to do that split thing that we were doing before. So this is T0 going out. This is T1 going out. But we have both T0 and T1. So I can do like a little white box here. Maybe. To say, hey, we have both. We'll fill it with white. Fill with white. And we'll do solid. Okay, so now this guy is N0. This guy needs to go back to being border. That, yeah. he only has half. So he'll get a little half here. RxN0, RxN1. Oops. So now at this stage, at the end of this stage, actually I should do it as when it actually accomplishes it here. Yeah. And I'll copy them along just to make it easy to visualize the completion of the overall progress. Okay, so at this stage we have 1, 2. I wish there's a way of doing like a, I guess maybe we could do like a half here. Let's do a half. That way we can visualize this fully. And this is going to be, instead of white, we're going to make it like gray, like mid-gray. That didn't do anything. So here you can go back to being white, but we're going to make this guy mid-gray. And we'll make this thing like that. We'll do mid-gray for that one. Okay. Oops. Oh, maybe we could fill it, the whole thing, and push it to the background. Maybe that would be an easier way of doing this. Yeah, let's do that. And then we just say, hey, you're down at the background. Oh. But we need to find like a better color than that. I like my current strategy here. So this guy can go up to be the whole thing. Oops. You need to go up, bro. And we'll do it up to 8. Because 8 is like, it's not terribly large to do manually to get a picture for it. And then, but it is large enough to be interesting. That's what I like about 4 bits. Okay, at the end here, we got that. Well, we don't know that yet, because we haven't done that. But we do know that this guy oh, he's the bottom. Yeah, I like that. He's at the bottom here. So this is T1. Why is this down here? It should be down here. And this is, yeah, that's why I did this diagram, because it's a lot clearer what's going on here. These are flipped. So it's sending T2, sorry, sending T1 to N2. And then this one's sending T0 to N3. So now what does our distribution look like? We have a choice in N0, and then we have these fragments here where we have N1 has the 0th part, and 3 has the 0th part. These have the even parts. So total, if we look at just this point in the game, so at this point in the game at 400, we had effectively one copy total of the file. At this point in the game, how many copies do we have? We have total, we have 2 copies, the original and the copy made at stage 400. At stage 400 over here, we have the original plus we have 3 halves. So we've already improved by an additional half just at this iteration here. And I think the algorithm I'm going to employ here is that we should maximize for the amount of chunks being sent until there's no longer a need for those chunks, in which case we start receiving. So it has to be a balance between sending and receiving, basically. But we should optimize for sending as most as possible until there are no longer receivers. And then we should basically balance sending and receiving. That'd be a fun algorithm to implement. All right, let's go ahead and copy these over. And we'll get to see the mathematical properties of chunking through this diagram, which will be nice. The problem I have with this is 800 is kind of not aligned. So I'm just going to move 400 and 800 out a little bit. Just give it a little bit more room. Alright. So this is going to say, hey, I'm going to go to, in this case, 4. And I'm going to send chunk 1 to N4. Receive the first chunk from N0. So now this guy has this pattern. So we want to transmit chunk 1 now. These guys don't have a choice. They have to transmit chunk. Oh no, 0 and 1. Okay. So it's going to be transmitting chunks 1 to N5. Copy this. It's not changing. And then this guy's going to receive chunk 1 here. should give him this pattern here. And then we'll need a little arrow guy going from here down to here. Then we'll just confirm we're sending to N5, N5 we're receiving from N2. N2 to N0, N3 to N1. Yeah. Okay, so then this guy needs to transmit 0. Oops, he needs to copy his thing over here. Let's copy that. I think we should actually grab this from here. Yeah. Transmit 0 to N5. This will be a question mark for now. This will be the same for here. Alright, so we got N4 going to N, or element 0 going there, yep. Element 0 from this guy going to 5, yep. Element 1 is going to 6 here. Sorry, element 1 is going to 6 from 2. This is from N1. 0, N5, N1, 0. Okay. This one is going from 2 to 6. And then 6 is from 2. And then we get this pattern here. This pattern's wrong. It's going to be 0 here. Oops. Alright. So let's do our arrow here. Can I get a little bit closer so that we like, can I turn this magnet shit off? How do I do that? Settings. I don't think there's a way of doing that. Okay, we'll do it here. Scoot this guy over as much as possible. Here. And then this guy's gonna go, oops, transmit 1 down to there, N2, N6, 1, yep, 0, 1, 0, yep, 0, yep. And then the final one is this guy's transmitting 0 down to N7. Should be like this. So this is going to be N7. Just pull it down a little bit. So we're coming from N3 and we're going to N7. If we do a little lining here, it's going to look like that. And then maybe I'll change the arrow's location based on which element. So this is the 0th element will be on the left. And then the 1 element will be on the right. And that'll kind of declutter the diagram a little bit. So 0 will be on the left. This is another 0, be on the left. This is the 3rd 0 here, be there. And this is a 1, which would be on the right. Maybe he shouldn't alternate. Maybe since he knows he's the original one, maybe he sends the first chunk. Now he knows that other guy can send. And then he just starts sending his second chunk until it's fully saturated. That might be the algorithm. Because then you'll have 2 concurrent branches. One, it's easier to analyze asymptotically too. So you have one branch that's sending the 0s, and then you have one branch that's sending the 2s. And they both kind of kick off at the same time. I think that might be the algorithm. So we'll bring this thing down here. We're actually going to be transmitting T1 to N4. So let's bring this over here. And we say, hey, you're actually going to be receiving 1. We'll move this down here. And we'll flip these here to be like that. So TX1 to N4, RX1. And I just need to fix my little arrow here. Point down here. Okay. Next iteration. So now we have every element has a part of the fragment. So we've hit like a certain point in this diagram. That's a unique point, which is like every machine now has at least one chunk. So now going to the next one, we're going to keep our algorithm, which is just send with your chunk until there's no one to receive it. And then you start receiving. Okay, so this guy is obviously going to stick with his method. So who doesn't have a T1? So this is at 800 here. Who doesn't have a T1 at this point? Well, N1, but N1's already sending. So some of them have to be receivers at this point. Everyone can't send because, I mean, at this point, everyone has a chunk to send, so they can't be eager senders. There has to be some like trade-off. What is a simple algorithm that would like balance the amount of senders and receivers? Because we've been able to send up to this point. Now we need to mix send and receive. So maybe we have an algorithm that's like stochastic. We just flip a coin and we either send or receive. I don't like that, but because it's not deterministic, but like let's just diagram it out to, because this diagram's meant to estimate the total theoretical throughput of chunking on by itself. Okay, so right now we have one up, one down, one up, one down, one up, one down, one up. Okay, so you have 1, 2, 3, 4, 5 for ups, 1, 2, 3, 4 for downs. So it's good that we're continuing to send down here. Okay, so who we're going to send down to? We can send it to N1. Let's try doing that, pairing off with our neighbors. That'll make the diagram a little bit easier to draw. So we're going to send T1 to N1. And then this guy has to receive that. So we're going to receive N1 here from N0. Yep. And now we have this guy complete. Oops. And the sender here, since this is 1, we'll do it on the right hand side like that. Alright. So N2 is still going to send. Element 2, and then N3 can receive that. So we're going to send to N3 here. And then here, we're receiving from N2. Oops. Sorry, this needs to go down here. So we're saying transmit 1 to N3 and receive from N2. So that'll look like this. Oops. And then this guy will actually have the full thing at that point. So we can eliminate all of that. This guy still has a partial. Oops. What's the next one? This guy's gonna send. He's gonna send his part down to here. Okay. 1, 1. Okay. We can do that. Oops. So you're going to transmit to N5 and you're going to receive from N4. Okay. And then we'll do the same thing here. Kind of like the symmetry of this. So it's going to transmit to N7 and he's going to receive from N6, and then this needs to continue over here. Alright, let's stack these up a little bit nicer. This needs to go out a little bit along with this, this. Oops. Okay. So at time 800, we're more than halfway there. And then let's finish up the thing here. So everyone needs to receive the T1s now. And there's more than enough people with T1s. So we got 1, 2, 3, 4, 5 people with T1s. And 1, 2, 3 that need to receive it. So two people are done. I'm gonna say the original two here are done. So they're just done. They're not gonna do any activities. This guy here is then gonna, so he's gonna transmit his T1, sorry, T0, TX0 to N2, and then this guy is gonna receive 0, sorry, RX0 from N3, and then that will give him the green light. Oops. Oh shit, I messed that up. Needs to be like this. My bad, my bad. Fix that up here. Can I, oops, rotate this? I can't rotate. And this is 0, so we're doing left side. These are all ones, 1, 1, 1, 1, yeah. 0, 0. So everyone will be done by this point. And we'll just need to copy these, which is going there. That looks about right. But we're going to rename these, so we're receiving from N5. And we're sending to N4. Actually, let's move all of these over a little bit. Oops. And then this is going to receive from N7, send to N6. Okay. Let's take a look at this, and then we'll do a mathematical analysis of it. So in the first one, it took us 1,200 seconds to complete this entire transfer. In the second one, it only took us 1,000. So by splitting by half, we're able to reduce the runtime by a fraction. I mean, it's definitely an improvement. What is the mathematical property of this? That's what I'm curious about. When we increase the amount of chunks, how significant of an impact is that on the runtime? Let's try to do an asymptotical analysis on this. less easy to analyze for sure. Well, we can plug in our data points and then try to extract out some type of pattern here. So T1 is still 0 seconds. T2, so if we just had 2 here, we would have transmit, receive, transmit, receive. It'd still be 400 seconds. T3, or say, let's just do T4. We'll put a question mark here because we don't know the algorithm yet. T3, I don't even know how long T3 will take. T4, we do know how long it's going to take. And T8 will be 1,000 seconds. So, sorry, 1,000. T3, say we just had 3 nodes here. We could copy this entire thing and I'm just going to do this just for experimentation. So say we have 3, or yeah, T4 is what we're trying to figure out. So we're going to delete everything except for 0, 1, 2, and 3. So all of this shit is gone. Including all of this. And we delete all of these. Okay, bam, 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 bam. Okay. Let's try to just do this one now. Using the same algorithm. So we first transmit to N1, and then we transmit down to, so these are the same pattern here. And then I have a T1 here. Everyone's able to transmit at this point, but 2 nodes have to receive. We have N1, N0, N1, N0. So we just basically need a trade-off here. So N1 is going to go to here. Which will satisfy this. And then this guy is going to send his down here. Oops. Like this. We can delete all this because I think all that's going to be unnecessary. And then this can be a last final step here. And then this will be what? And we don't transmit obviously while we're receiving there. We don't transmit here. So transmit, receive, full. Transmit, receive, still have. Transmit, receive. So it's T1, and we're sending it to N3. This thing's receiving it from N2. We're sending it to N1, receiving from N0. This guy's, we're going to send this to N2 and receive it from N3. And then he's a full after that. So at 800 seconds for N equal 3. Sorry, N equals 4 is 800. Oh, which is interesting that it's the same value so far. Wait a minute. Yeah, same value because that's rounded at ceiling. Okay. And if n is equal to 3, let's try that one. So we're just going to knock out 3 here. So that means that all these operations are like not important. Boom, boom. Okay. It should be 800, yeah. So we send 0 here, we send 1 down to here. And then I'm just going to get this guy out of the loop and say he's going to receive from there T2. This guy can't do anything. And then these guys trade back and forth. So he's going to receive his T2 from here. Should be this direction here. Oops. N is equal to 1. So we're receiving from 2, and we're sending to N1, part 1. And then he has to receive from N1. And he has to send T0 to N2. So I'm starting to think of like how this can be represented mathematically. These are a bunch of example situations. I think this T3 has like got my brain to think more about the overall capacity of the system. And maybe if we can like solve for these smaller examples, that'll generalize to the larger example. Okay, so send to T1, send to T2, receive from there, receive from N2, send from there, send to N2, receive from there. Okay. And that took 800 seconds as well. So 3 is also 800 seconds. Two, I imagine, is going to be 800 seconds because it's it's 400 seconds, yeah. And then 1 is 0 seconds. So everything's the same up until we get to T of 8, where we start to see an improvement. Oops. Yeah, these are a little bit off. Maybe we go down to a quarter chunk. Do you think we would see a benefit? It would obviously be a larger benefit, but would I be able to see like a mathematical rule if I did a quarter chunk? An obvious mathematical rule? I do not know. So the benefit of this is that we can start sending earlier on nodes. We have like a head start on sending. Because at this point, we're identical. We have a sender and a receiver, identical. At this point, identical. Sender, sender, receiver, receiver. At this point, no, we're not identical because this is at 200. So, interesting. Let's divide the time up a little bit further. So I'm going to say 200 here. Well, I don't need to do that. I can already like imagine my head that point. And we need to delete these numbers because they're not relevant to this situation. 0, 1 can be. Let's go ahead and delete all these. So they got garbage in them. They're in the wrong position. Oops. So I'm going to diagram out here how many are active. So we have 2 active at this point. Let's do white here. Let's go over here. So it's 2, 2, 4. How many nicks are active? That's really what. How many nicks are saturated? 4. 8. 8. And then 0, because we're done. Let's get these a little bit better aligned here. So let's go and grab all of these numbers, and we will can I align these like bam? Okay, good. So I'm going to copy them, pull them over here, and our spacing's a little bit different here. So what I'm going to do is I'm going to pull 0 over here, pull this one over here, reselect them all. Maybe I can do my alignment thing. Do like that alignment and then that? No. It's more spacing than it is alignment. These guys. There we go. Close enough. Okay. So here we have 2. Here we have 4. Here we have 8. Here we have 8. Here we have 6. Here we have 0. And then this guy's obviously 0 as well. So we went from 2 to 4 to 8. Same progression here, 2 to 4 to 8, but we didn't have the time. So we got to 8 in 400 seconds. It took them 800 seconds to get to 8, to full saturation. So it's about dropping the time it takes to get all of the NICs saturated, either sending or receiving. And it takes 800 seconds to do that on the left-hand side. It takes 400 seconds to do it on the right-hand side. And then the other property is that once everything's fully saturated, on the left-hand side, we drop to 0 immediately, whereas on the right-hand side, there is a lag time of at least 1 frame. I'm calling these little units of 200 seconds frames, because if you are at a state where you're fully saturated, then all of the NICs are saturated. That means after that step, there can only be 1 additional step to then backfill everything. So then why did I take 2 steps here? Maybe because it takes it takes 2 steps because there's 2 fragments. If you have n steps, it would take n fragments. Or if you had n fragments, it takes n steps. So this is a sweet spot. I'm going to call this the sweet spot, where all of the NICs are fully saturated. It's kind of like this part of the transfer here, where we're at the sweet spot. So we got to the sweet spot at 800. They got to the sweet spot at 400. I don't quite understand this fall off. You would think that if we're at the sweet spot, it would take the same time to do the full transfer, the same amount of data. Oh, but we did less data transfer over here, so then we have to make up for it on the last step. That's what it is. Yeah, the sweet spot, we can transfer half of the data. So the total data that needs to be transferred is let's do an equation for that. Total data needed to be transferred. And we'll call this D. D of N. I can delete this, right? Yeah. Total data need to be transferred is D of N. N minus 1 500 gigabytes times n minus 1. So if we were at 2, that'd be 500 gigabytes needs to be transferred. If we're at 3, yep, be 1,000. 4 would be 150. So at 8, let's do our same table here. Where we do this, t equals 0, all that stuff, yeah. So t of 1 is pretty easily 500 gigabytes times 0 is equal to 0 GB, capital B. T of 2, 1, 500. Three, 4, 8, 1,000. Three, 4, 8, 1,000. So 3 would be 2, 3, 8 would be 7, 999. This will be, sorry, 500, not 5,000. This will be 1,000. 1,500. 3,500. And then 999 times 500. 499,500. Yeah. Alright. Sorry, I was muted there. I don't know why I muted myself. T sub n is equal to n divided by 2. It's not really n divided by 2. Because they can be done in parallel. Those are the units of parallelism. It's the remainder. N mod 2. No, because then... So everyone can receive, even though there's only one transmitter, just say theoretically one transmitter can send to all the recipients, then it would be 400 seconds. But we're under this situation of all NICs are at full utilization immediately. A NIC can only transmit TX to one RX at a time. A NIC can TX even if it doesn't have data. Impossible. This is not possible, but represents a limit on perf. So basically, everyone can receive, but half of the population needs to be transmitting, and then the other half can receive, and then the other half can transmit. So it's gonna be 2 times the it's not even parameterized based on n. I guess it has to have something there based on n, but it's 2 times transfer time. So that applies to all cases except for T2 and T1. So where does n come into play here? One-time transfer. say a hard limit. Alright, we need an equation for this. 2 times t, but how do we factor in n? It's probably going to be a times something, n. And it feels like a mod. N mod 2. So that'd be 0, 1, 1 times, replacing this 2, t times n mod 2 gives us 0 and 2, but then when we hit 800 seconds here, it goes back to 0. So it would alternate between 0 and 400 seconds, which isn't what we want. This would be 400 here. Let's ask AI because I'm not familiar with how to do this. So I have a function of n, we'll call it f of n, where the resulting value is 0, f of 0, 0, f of 1 is 1, f of 2 is 2, f of 3 is 2, and so on. We'll say f of 4 is 2. What is the body of the function? Yeah, I mean, I would use int. I would use min. Piecewise, that works too. Is there any way to implement this using okay. T times min n or 2? So in this case, min n, or 2 would be n, which is 1. 1 times t. So this needs to be minus 1. So this would be 0 or 2. No, we don't need a minus 1. What am I talking about? Oh yeah, because t, okay, yeah, 1. So it'd be 1 minus 1, which is 0, 0, okay. And then we get to 2, min of 2 or 2, minus 1 would be 1. That works out 3. Would still be 2 minus 1, 1. So this needs to be 3. The min of that, and we'll say times t. Let's put that down. And we'll just do that here to demonstrate that that is correct. Okay, so min of 1 and 3 is 1 minus 1 is 0. So this all collapses to 0 times t. Min of 2 and 3 is 2 minus 1 is 1. And then these are all going to be 3 minus 1, which is 2. 2. 2. 2. So 800 seconds is the theoretical maximum performance we could get. It's impossible to achieve, but we can approach it. It's like a limit, like a mathematical limit. And we can kind of demonstrate that here. So if we apply this to 1,000 here, then it would be 2 times t, which is 800 seconds. And you might think, oh, that's such a big number. Well, the total data needed to be transferred is this amount. So if we just go here, can I just copy this maybe? Yeah. Delete everything. And then grab here, the total data need to be transferred, divided by the number of servers that can do the transferring. Times the bandwidth, which is what? 10 gigabits we'll do the, I guess it doesn't matter, times this, which is 10 gigabits per second. So if we bust out our calculator here, full screen that. Okay, so we say, hey, 1000 times 10 divided by 8 would equal this number of gigabytes per second. 1250 gigabytes per second, which if we do the math on this would come out to, delete that, 400 seconds. But a transfer requires both a sender and a receiver, which is why our equation should be different here. This should be 5 gigabits. So if we do 4 divided by 1000, wait a minute, what is 1000 times 5 divided by 8? 625. That makes sense, be half of that. And that'd be 800 seconds, yeah. Okay, that works. Alright, I'm going to get the hell out of here. When I get back, we'll do some more work on this diagram here for 16 nodes, and then try to derive a formula for 1,000 to be able to calculate how much time it would take for 1,000 nodes in this configuration, and then try to drive down to a quarter chunk size, and then take that to its limit and see how far we can get. Cool. All right, I'm going to get off then. I'll be back later tonight. Cool. See ya.